I'm Bloemfamay and welcome to my lecture series on computer and network security. In the previous two videos, I talked about how to distribute private keys using symmetric encryption. An alternative approach to distribute private keys consists of using asymmetric or public key encryption. This is what I will talk about in this video. And one of the first and most simple approaches to symmetric key distribution using asymmetric encryption was put forward by Ralph Merkle, an American computer scientist and also one of the inventors of the Merkle-Damgard family of cryptographic hash functions. And the scheme is very simple. Two hosts want to exchange a symmetric key, in this case host A and B. Host A sends its public key together with an identifier to host B, and host B responds with an encrypted message, encrypted using the public key of A and some session key. Clearly, this system works as only A will be able to decrypt this message, as only A has access to its private key. Recall, in public key encryption, the public key can be shared with anyone and used by anyone, but only the one that owns the private key will be able to decrypt messages that have been encrypted with the public key, or the other way around. So now A and B share a session key without having to have shared a master key beforehand. Sadly, however, this very simple and elegant method is vulnerable to so-called man-in-the-middle attacks. And here you see how such an attack works. Let's assume Alice, A, and Bob, B, want to securely exchange a private session key. Assuming the same method as before, A will send its public key and some identifier to B. However, Dart is an attacker who is able to eavesdrop on and intercept messages exchanged between Alice and Bob. Dart can now exchange the message sent by A with another message sharing its own public key with Bob together with the identifier of A. Since Bob has no way of knowing if this key, PUD, is actually Alice's public key or not, he will assume it is valid. He will use the public key provided to him, PD, to encrypt a session key KS. Dart again intercepts the message and is able to decrypt it as he owns its own private key PRD. Dart can then send the same session key but encrypted with A's public key towards Alice. Now, not only Alice and Bob share this session key KS, but also Dart has access to it. This clearly shows a problem with using public key encryption to share private session keys. And in 1976, Diffie and Hellman jointly invented the first public key cryptography algorithm, called Diffie-Hellman key exchange. If you recall from the videos on public key encryption, you know that Diffie-Hellman is only used for key exchange, so it cannot be used for other applications such as encryption. And while RSA relies on the fact that it's computationally very difficult to factor a large number into primes, Diffie-Hellman relies on another concept, namely that it's very difficult to calculate discrete logarithms. And a discrete logarithm is defined as follows. The exponent I is the discrete logarithm of b for base a modulo p if b equals a to the power I modulo p. And let's take a look at how we can use this difficulty to calculate discrete logarithms to create a key exchange method. So in Diffie-Hellman, the two parties first share a public pair of values q and alpha. Q is a prime number and alpha is an integer and a primitive root of q. How do we define a primitive root? Well, a unique exponent I exists for every integer b less than q, so that b equals alpha to the power I modulo q. If such a unique integer exists for every value b, then alpha is a primitive root of q. Then both parties use q and alpha to generate their private and public keys. The private key is very simple. It's a random integer less than q. So both a and b just generate a random integer, xa and xb. Second, the public keys can be calculated from the private keys alpha and q. Specifically, the public key y equals the value of alpha to the power of x modulo q. It is clear to see that actually the private key x is a discrete logarithm of the public key y for a base alpha modulo q. Subsequently, the parties exchange their public keys, so a sends ya to b sends yb to a, and they can calculate the shared secret key k. Namely, a calculates it with the public key of b to the power of its own private key modulo q, and b calculates it with the public key of a to the power of its own private key xb modulo q. It can be shown that both operations result in the same shared secret key k. So here they can exchange the secret key k without actually sending it over the network. They only have to exchange or send their public key. And let's take a closer look at the security of the Diffie-Hellman key exchange algorithm. An attacker will have access to all the public information that is shared over the network. This includes q, alpha, and the two public keys ya and yb. The private keys are never transmitted, so they are safe. However, an attacker could now try to calculate the private keys. As I said, the private keys are the discrete logarithm of the public keys base alpha modulo q. So, using this knowledge, an attacker could try to calculate the discrete logarithm of the public keys. However, the security of Diffie-Hellman relies on the fact that it's easy to calculate the exponentials modulo the prime number, but it's very difficult to calculate the discrete logarithms. And as such, as long as no technique is found to easily calculate discrete logarithms of large numbers, Diffie-Hellman is considered secure. However, if we use Diffie-Hellman in the same way to exchange session keys as I explained before, we still run into the same problem of a possibility for a man-in-the-middle attack. Here you see the man-in-the-middle attack I explained before adapted to Diffie-Hellman key exchange. As you can see, an attacker will still be able to intercept messages and replace the public key of A, namely ya, with its own public key to then get access to the session key. So to make this type of key exchange secure, we need a way first to securely exchange public keys and to verify the authenticity of public keys. So this is very important.